Okay, let's unpack this. Think about how often you just use someone's gaze, right, to figure out what they're thinking or maybe what they're looking at.
It's fundamental, yeah. So much of our interaction relies on it.
Absolutely. In a conversation, you're instinctively following their eyes to see, like, what object they're pointing towards mentally.
Or in a group, who's paying attention to who, it tells you a lot about focus, intent, social stuff.
Exactly. So for AI systems trying to understand us or interact naturally, predicting where someone's looking, that's got to be huge.
It really is. And technically, it's a pretty tough problem for AI.
How so?
Well, the system needs to figure out two different things at once. First, it needs details about the person, especially their head, the pose, maybe even the eyes, because that dictates the gaze direction.
Okay, makes sense. The person's orientation.
Right. But second, it also needs to understand the whole scene around them. What are the possible things they could be looking at? Objects, points of interest.
Right, the context is crucial. So how did researchers used to tackle this? What was the old way?
So the typical approach for a long time involved these pretty complex setups. They call them multi-branch pipelines.
Multi-branch. Okay, what does that mean?
Imagine like separate processing units. You'd have one part, an encoder, just looking at a cropped image of the person's head, trying to figure out the gaze direction from that.
Okay, a head specialist.
Exactly. Then you'd have another separate encoder processing the entire scene image to understand the environment.
So two main pathways, head and scene.
Usually, yeah, and sometimes even more. Some methods added extra branches for things like depth maps, 3D information about the scene.
Ah, okay.
Or maybe the person's estimated 3D body pose. And often, that extra information came from other AI models running first.
Wow, okay, that sounds complicated because you're building this big machine with lots of separate specialized parts.
It really was. A lot of engineering effort went into designing each branch, figuring out how to best combine the information, the fusion part.
Fusion, right. How do you stick the head info and the scene info together intelligently?
Precisely. And you often needed complex training setups, maybe trying to teach each part separately first, or having multiple goals for the model to learn. And importantly, these models ended up with a ton of learnable parameters.
Parameters being the things the model actually learns during training.
Yeah, the knobs it tunes. We're talking like potentially over 50 million parameters that needed to be trained, often on relatively small data sets too, where people had manually marked where someone was looking.
Okay, that does sound like a bottleneck. Complex design, complex training, lots of parameters, maybe limited data. So where does this Gaze-LLE paper come in? You said it's a revolution.
Well, Gaze-LLE basically throws a lot of that complexity out the window. It takes a very different, much more streamlined approach.
How so?
Instead of building all those specialized encoders from scratch, it leverages these massive general-purpose AI models that have already been trained on enormous amounts of image data.
Ah, the foundation models you hear about.
Exactly. Models like Dinos 2. They already have a really rich understanding of visual information. Gaze-LLE's core idea is, can we just use that existing knowledge and build something much, much simpler on top specifically for gaze?
Okay, so this is where it gets really interesting, right? Our mission then for this deep dive is to really get into how Gaze-LLE works differently, understand its specific design, why those choices matter based on their analysis, and, why it's getting these top results while being so much simpler.
Precisely. We need to look at how it uses these foundation models, its architecture, and the evidence that backs up this sort of paradigm shift for gaze estimation.
All right, let's start with that aha moment, using foundation models. How does Gaze-LLE actually do that?
Okay, so the main idea is using a powerful pre-trained vision model, they use Dino V2 in the paper, as the main way to understand the scene.
Dino V2, that's one of the big self-supervised models from Meta, right? Trained on tons of images.
Correct. It learns really robust, general visual features without needing explicit labels for everything. It just learns from the data itself. So Gaze-LLE takes this powerful Dino V2 model, and this is the crucial part, it keeps it frozen.
Frozen, meaning?
Meaning they don't train the Dino V2 part at all for the gaze task.
Wait, really? So the biggest part of the model, the part that understands images, isn't learning anything new about gaze?
Exactly. It's used off the shelf. Its parameters, its learned knowledge about images remain fixed. Gaze-LLE just feeds the scene image through this frozen Dino V2 and takes the output features it produces.
So you're basically borrowing the image understanding power from this massive pre-trained model.
You got it. You get these rich feature tokens representing the scene's content, capturing lots of semantic information. It's a huge departure from training everything specifically for gaze.
Okay, that makes sense. Conceptually leverage existing power. But the paper points out something really counterintuitive, doesn't it? They found that just taking Dino V2 and plugging it into one of those old multi-branch architectures, it didn't work well.
Yeah, that's a super important finding they highlight. Table 1 shows it quite clearly. If you just swap in Dino V2 into an old-style model with separate head and scene branches, it actually performs worse than the original models that used supposedly weaker backbones.
Why would that happen? A stronger backbone should make it better, shouldn't it?
You'd think so, but it shows that it's not just about the raw power of the features. It's about how you use them. Those old architectures were designed and tuned for the kind of features their original encoders produced, maybe more convolutional, more focused on specific things.
Ah, okay.
Dino V2, being a transformer trained with self-supervision, gives you features with different properties, probably more global context, different kinds of semantics. Shoving those features into a structure not built for them well, it doesn't work effectively. You can't unlock the power.
So you need an architecture specifically designed to work with these foundation model features.
Exactly. And that leads us right to Gaze-LLE's own architecture, which is much leaner. Tell us about the learned Gaze decoder.
Right, so this is the part that is actually trained for gaze. It's much smaller.
Much, much smaller. So you take the scene features from the Frozen Dino 2. Those go into this small, trainable gaze decoder. This decoder is basically the only bit where the learning happens for the gaze prediction task.
So Dino V does the heavy lifting of understanding the image, and this little decoder just learns to translate that general understanding into a specific gaze map.
Pretty much. And a really key design choice is how and when information about the specific person, their head position, gets incorporated.
Right, you need to tell it whose gaze to predict. How does that work? Did they try feeding it into Dino V2?
They mentioned that prior work often tried things like that, maybe adding the head location as an extra input channel to the main encoder. But Gaze-LLE found it works much better to add the head info after the Frozen Dino V2 has already done its job processing the scene.
Interesting. So process the whole scene first with the big frozen model, then bring in the person-specific head location. Why is that better?
Well, their analysis backs this up. Trying to force the Frozen Dino V2 to understand head location input didn't really leverage its strengths. It wasn't trained for that specific kind of input guidance.
Right. It was trained for general image understanding.
Exactly. But by adding the head information later into the features that come out of Dino V2, the learned decoder, the part that is being trained for gaze, can learn specifically how to use that location information effectively to predict the target.
Okay, so how do they actually add that head info? Do they still have like a mini head processing branch?
No, and this is another really elegant simplification. They call it head prompting.
Head prompting?
Yeah. Instead of a separate head branch, they create a small head position embedding. It's basically a learned code that represents where the person's head is in the feature map produced by Dino V2.
Okay, a location code.
And they just add this learned code directly onto the scene feature tokens that correspond to the head's location.
Huh. So you're literally just nudging the scene features in the head region, telling the decoder, focus here.
That's a great way to put it. You're prompting the decoder. It's a very simple but effective way to condition the output on a specific person without needing a whole separate processing pipeline for the head.
And what processes those prompted features?
The decoder uses a small transformer module, which makes sense, right? Transformers are good at seeing relationships across the whole input.
Yeah, global context.
Yeah.
So it can relate the prompted head location to potential targets anywhere else in the scene features.
Precisely. The transformer processes the scene features plus the added head prompt together.
And then it outputs the final gaze map.
Yep, it decodes that into the heat map, showing gaze probability across the scene. And sometimes also predicts if the gaze is inside or outside the frame. The key innovation here is this minimalism. Frozen base, tiny learned transformer decoder, simple head prompting. It replaces all that multi-branch complexity.
It definitely sounds cleaner. And you mentioned the paper really digs into why these choices work, the academic validation part.
Absolutely. The analysis sections are crucial. They didn't just propose this, they systematically tested alternatives to show their design was the right way to go, especially when using these foundation models.
Like testing where to put the head info. Before or after the frozen part?
Yes. Table 2 shows clearly adding the head prompt after the Frozen Dino V2 features works much better than trying to modify the in-output before. It really validates keeping the foundation model untouched.
And the choice of decoder, Transformer versus, say, a standard convolutional one.
They tested that too. Same table shows the transformer decoder was significantly better than a convolutional one when using Dino v2 features. It suggests that to really leverage the kind of global semantic features from a model like Dino v2, you need a decoder that can also think globally, like a transformer. Convolutions are more local.
Makes sense. What about ditching the separate head branch entirely? Did the analysis confirm that was okay?
Yes, that's another big takeaway from their ablations. With the transformer decoder and the head prompting, that dedicated head branch just wasn't adding much value anymore.
So the Dynav2 features themselves, plus the prompt, already contain enough information about the head's orientation for the decoder to work with.
Apparently so. The transformer decoder, guided by the symbol head location prompt, can extract what it needs from the rich scene features provided by Dino v2.
So the prompt is mostly for telling it which person to focus on if there are multiple people?
That seems to be its primary role, yes. Essential for disambiguation. Though interestingly, they found that even without the prompt in single-person scenes, the model still did okay.
Really?
Yeah, suggesting the scene features and the transformer decoder implicitly capture some gaze information just from seeing ahead. The prompt just makes it explicit, predict for this person.
That's quite cool. Did they look at where in the decoder to add the prompt? Does it matter if it's early or late?
Ah, yes, another nice analysis detail. They found that adding it earlier in the small decoder gives a tiny performance boost, but adding it later is almost as good performance-wise and potentially much more efficient computationally.
How so?
Well, if you add it later, the initial layers of the decoder, which process the scene features before the prompt, could potentially be run just once for the whole scene, even with multiple people. Then you just branch off of the person's specific prompt later. Saves computation.
Clever. Okay, so the analysis really seems to nail down why this specific recipe, frozen foundation model, transformer decoder, post-encoder head prompting, works so well.
Exactly. It's not just simpler conceptually. The data shows these choices are empirically better for leveraging foundation models for gaze.
So let's talk results. What does this all mean in practice? Why should people care about Gaze-LLE?
Okay, the payoff is pretty huge. First, performance. It achieves state-of-the-art results. Better accuracy than previous methods on the main benchmarks like gaze follow, video attention target, child play.
So higher scores on things like AUC and L2 distance error.
Yep, consistently better across the board, according to their table, so it's more accurate.
Despite being simpler. That's impressive.
And that simplicity leads to massive efficiency gains. The number of learnable parameters, the part you actually train, it's tiny compared to the old methods.
How tiny?
Around 2.8 million trainable parameters in their model versus, like we said, maybe 50 million or more in some older complex systems. That's a huge reduction.
And fewer parameters usually means faster training,
Yep.
right? Less data needed, maybe.
Exactly. They report achieving these state-of-the-art results in under 1.5 GPU hours of training. That's incredibly fast compared to potentially days of training for older complex models. It makes research and development much quicker.
Okay, that's a practical game changer. What about generalization? How well does it work on data it hasn't seen before?
This is maybe one of the most impressive parts. It generalizes extremely well. If you train it on one data set, say gaze follow, it performs really well on other completely different data sets like video attention target or child play without any extra training or fine-tuning.
Wow, really? So train once, deploy potentially in many different environments.
Pretty much. It even beats older methods that use specific techniques designed for adapting between data sets.
Why does it generalize so well?
The thinking is it's down to those robust general features from the frozen Dino v2, which captures fundamental visual understanding, combined with a small decoder, which is less likely to overfit to the specifics of just one data set.
That sounds incredibly useful for real-world use. And does it handle practical issues like imperfect head detection?
Yes, they check that too. It still works well even if the head locations are provided by a standard object detector like YOLO5, not just perfect ground truth annotations, which is crucial for real applications.
And inference speed. Is it fast when actually predicting gaze?
It's faster than methods that need extra inputs like depth maps, which require running another model. And crucially, it scales really well when you have multiple people in a scene.
How come?
Because the expensive part running the big Dino v2 encoder only happens once for the whole image. Then you just run the very small fast decoder multiple times with the different head prompts. The overhead per person is minimal.
Okay, so let's recap the benefits. More accurate, way fewer parameters to train, drastically faster training, amazing generalization to new data, works with real-world inputs like detected heads, and efficient for multiple people. That really covers a lot of bases.
It really does seem like a significant leap forward.
Are there any downsides or limitations mentioned?
They do point out a couple of things. Obviously, the performance depends heavily on the quality of that frozen foundation model you use. Garbage in, garbage out, to some extent.
Right, you need a good general encoder like Dino V2.
And while it's super efficient in terms of training and learnable parameters, you're still running a large foundation model at inference time, which might still be too heavy for, say, tiny embedded devices with very limited compute.
Although you mentioned the cost is shared if you're analyzing multiple people.
Exactly. And they also point out that the whole Gaze-LLE framework is modular. As newer, maybe faster, or even better foundation models come out, you could potentially just swap out the frozen encoder and benefit immediately.
So it's well positioned for the future. Less a fundamental flaw, more a dependency on the current state of foundation models.
That seems fair, yeah. It sets up a strong template for building on top of future advancements in general vision models.
Okay, so bringing it all together then. Gaze-LLE offers this really compelling new way to do gaze estimation. Forget the super complex, custom-built multi-branch monsters.
Right. Instead, take a powerful frozen general vision model, add a small, smart, learned decoder, a transformer seems best, and use this elegant little head prompt trick to tell it who to look at.
And the result is simpler architecture, drastically fewer things to train, way faster training, top-tier accuracy, and much better generalization and practicality.
It really feels like a paradigm shift, moving away from hyper-specialized models towards leveraging these big general AI components with just a thin layer of task-specific learning on top.
Which could make building these kinds of systems much easier, faster, maybe unlock new uses. You mentioned applications.
Yeah, potentially in better human-computer interfaces, robotics, or getting deeper insights into human behavior and social dynamics. They briefly mentioned things like autism research context, where understanding gaze is critical.
It's definitely exciting stuff. It leaves you wondering, if this approach works so well for gaze, taking a general model and adding just a little bit on top, where else could this work?
That's the big question, isn't it? Could this minimal task-specific learning on a frozen foundation approach simplify other tough computer vision problems?
Well,
Or even problems outside of vision?
and that ability to efficiently track multiple people's gaze, maybe that's a step towards AI that can actually understand complex group interactions, not just individuals. Lots to think about there.
Definitely. It opens up some really interesting avenues for future research and applications.